All right, so today we're looking at second page of the Lilac Notes. It says energy in the Earth's atmosphere. Energy in the Earth's atmosphere. All right, so where the Earth's surface gets most of its energy from is from the sun. And we call that energy insolation. Now, when I say the word insolation, you're probably thinking of the word insulation, not the word insulation. You're like, what? What's that? All right. Normally, when you hear the word insulation, what you're thinking about is like that pink foamy stuff they put in your houses to keep it warm. That is insulation spelled this way. All right. What we're talking about today is insolation spelled that way. Right? Now, while they sound very similar, and at first glance they look, quite similar, and they both have to do with energy, they mean two different things. Insulation with a U is the stuff that you put in the walls of your house to keep it warm. All right. Insulation with an O is what we're talking about today. And insolation with an O stands for incoming solar radiation. So insolation with an O is incoming solar radiation. So basically it's sunlight. All right, sunlight. So the Earth's surface gets most of its energy from sunlight. All right. So insolation, incoming solar radiation, the portion of the sun's energy that reaches the Earth. All right. Now, the sun gives off a variety of types of electromagnetic energy, ultraviolet, infrared, visible light, and so forth. Most of the insolation that we get from the sun falls in the visible range. We do get some infrared, and we do get some ultraviolet, but a lot of the ultraviolet gets blocked out by this Earth's ozone layer. It blocks out a lot of the ultraviolet rays. All right, so what we mostly get is visible light. Now, the thing that determines primarily how much energy, how much that sun's energy we get is the angle of insolation, all right? The higher the sun is in the sky, the more energy the Earth receives from the sun. So, when the sun when the sun's rays are coming more or shining more direct on a surface like that, that surface heats up more. When the sun's rays are coming at a lower angle like that, what happens in that case is the energy spread out over a larger area. So when the sun's high in the sky like that, where it has a big angle of insolation, that's when we get the most amount of energy to your surface. When the sun's lower in the sky, the energy spread out over a larger area. As a result, each little square inch of surface gets less energy, and the conditions are going to be cooler. So how high the sun is in the sky, or the angle of insolation, is the main thing which determines the temperatures at the Earth's surface. Okay? Now, there's three things that determine how high the sun is in the sky. And one thing is your latitude, right? Typically, if you're near the equator, the sun's going to be higher in the sky. If you're near the poles, the sun's going to be lower in the sky. That's why it's cold at the poles and hot at the equator, right? So at the equator, bigger angle of insolation. At the poles, lower angle of insolation. Right? The other thing is the season, right? During the summertime, the sun's higher in the sky. If you notice in the wintertime, the sun's lower in the sky, and that's exactly why it's hot in the summer and cold in the winter, because the sun's higher in the sky in the summer and lower in the sky in the winter. And the third thing that affects the angle of insolation is the time of day, all right? In the morning, the sun's low in the sky, and it's relatively cool. In the afternoon, the sun's high in the sky and is substantially warmer. and then in the evening the sun gets low in the sky again and it cools down. All right. So the latitude, closer to the equator, generally speaking, the higher the angle of insolation. The season, in the summertime, the sun's higher in the sky, so you get more insolation. And the time of day, around noon, is the sun's highest in the sky, and we get the most amount of insolation. So those are the things that affect the angle of insolation. All right. Now, some other things that affect how much energy we get from the sun. Another thing is what's in the atmosphere. All right. So when the sun's rays are coming down, sometimes the atmosphere is not clear. You may run into clouds, or you may run into aerosols. Aerosols are like little dust particles or liquid droplets in the air. Like an aerosol can. If you have a can of hairspray and you kind of spray it towards the light, you can see like little droplets. That's why it's called an aerosol cans, because it's spraying out little droplets. But anyway, so if there's clouds or there's aerosols, like little particles floating around in the air, what happens is the sunlight can hit it. Some of that will get reflected back in outer space, or it can hit the aerosols and it can just bounce in a bunch of different directions and scatter. So either one of these scenarios, what's happening is not all the energy is getting to the Earth's surface. A lot of it's ending up going other places. So the cloudier it is or the hazier it is, not as much energy gets to the Earth's surface. And so that's going to decrease the amount of insolation we're getting. Another thing that can affect how much insolation the surface keeps is what the surface is like. All right? If the surface is dark and rough, then when the insolation hits the surface, most of the energy is going to be absorbed, and only a small amount is going to be reflected back in outer space. Whereas, so this would be like, a dirt or something like dirt or blacktop driving. It absorbs a lot, but only reflects a little bit. Whereas if the surface is light colored and smooth, a lot of the insulation is going to hit the surface, and a lot of it's just going to bounce back up in the atmosphere. So it's not going to stay at the Earth's surface. So light colored and smooth, it's just going to bounce off and go back up into space. Another thing that can affect how much insolation you get is, again, with the angle of insolation. Now, one thing about the angle of insolation is when the sun's coming at a low angle, it spreads the energy out more. So that's what we talked about back here. But another thing about it, when the sun's coming at a low angle, it gets reflected better as well. Things reflect more when it's coming at a low angle. If it's coming in at a high angle, it's going to get absorbed more. The analogy I like to use here, let's say you're at the beach and you pick up a nice flat rock, all right, and you go to skip the rock, all right. If I take that rock and I come at a low angle like that and skip it, it skips off the water, right? Does a good job of like reflecting off the water. If I take that nice flat rock and I throw it straight down in the water, it just goes blub, 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 blub. It goes straight down. It basically is getting absorbed. So when the sun's coming at a low angle, it bounces off more easily. If it's coming at a high angle, it gets taken in more. Okay. So like in the wintertime, it's cold for several reasons. One, the sun's lower in the sky, so we're getting the energy more spread out. Also in the winter, there's lots of snow, so the energy that is getting to the surface, a lot of it's going to get reflected. And also because it's coming at a low angle, a lot of it's getting reflected for that reason too. So there's a variety of reasons why it's cold in the wintertime, or why the low angle results in colder temperatures. All right, so that's the energy that reaches the surface. Now, once the energy hits the surface, what happens to it? All right. Now, energy hits the surface. Some of it gets reflected, but some of the energy is going to get absorbed by the ground. All right. The ground absorbs it, the ground heats up, and then the ground starts to give off energy. Right? So like on a sunny day with a blacktop driveway, the sun hits the blacktop driveway, the driveway heats up, and then if you put your hands over the blacktop driveway, you can feel the heat coming off of it. Right? This energy radiating from the earth. Right? That energy that the Earth gives off is what we call terrestrial radiation. All right, so it's energy radiated or lost by the Earth. Now, the energy that the Earth gives off is not the same type of energy that it got from the sun. Because the energy that we got from the sun, the insolation, is mostly visible light. Right? Visible light hits a blacktop driveway, the blacktop driveway warms up, the blacktop driveway does not glow at night. Right? It doesn't give off light, but it's still giving off energy because I can feel the heat coming off of it. So the visible light hits the surface. Right? Visible light has a shorter wavelength. Visible light will hit the surface. The ground absorbs it, and then the ground gives off terrestrial radiation, which is infrared energy. All right, so infrared energy is basically heat energy. It's a type that you can't see, at least we can't see. So that has a longer wavelength. So we get relatively short wave visible light from the sun. It hits the surface heats up, and then the surface gives off long wave infrared radiation. Right? Now, not all surfaces radiate energy the same. Darker colored surfaces radiate energy better than light colored surfaces. So that's why in that lab we did a while back, we said a good absorber is a good radiator. Because like back here, we're saying that the dark colors absorb insulation very good, but also dark colors radiate energy very good. If it takes the energy in very easily, it gives off the energy very easily. Now, if we are located on the moon or a place that does not have an atmosphere, this energy would just go off into outer space, all right? But lucky for us, we have an atmosphere, and what happens is a lot of the energy that goes off, that would head off into outer space, gets trapped in our atmosphere and warms it up. Right? And that's what we call the greenhouse effect. Substances allow visible light to pass through, but trap infrared, as a result, warming the air. Now, the reason why it's called the greenhouse effect is that's how a greenhouse works. A greenhouse has glass walls and glass ceiling, and what happens is it lets the visible light pass through it. The visible light passes through, hits things inside the greenhouse, which warm up. When those things warm up, they then give off terrestrial radiation, which is infrared. But the thing is, infrared doesn't pass through the glass very easily. So the infrared energy gets trapped inside the greenhouse, and then the air in here warms up. All right. So a real greenhouse, what they use that for is, if it's like February or March and you want to start growing some plants, but it's still cold outside, you'd use a greenhouse to warm the conditions up inside so you can start growing plants. Now, even if you've never been into an actual greenhouse, you've experienced the greenhouse effect. That's why the greenhouse effect is why you don't leave your dog in a car in a sunny day, because the exact same thing happens in a car. All right, so there's your car. There's your window. What happens is the sunlight travels through the window. It heats up the seats and stuff inside your car, the seats and the dashboard and stuff. Those things give off infrared energy, and that infrared energy cannot travel through the glass, and as a result, it gets trapped inside there, and it makes the temperatures inside your car very hot. That's why even if it's like 75 degrees outside, you don't want to leave your dog in the car in a parking lot if it's sunny outside, because the temperatures inside there will heat up very quickly because of the greenhouse effect, and it might be like 120 degrees in there when outside the temperature's fine, because the sunlight's getting in, but the heating up the seats, but the energy radiating off the seats and stuff just gets trapped in there and makes the air in there really hot. That's the greenhouse effect. Now, obviously there's not like a big glass shell surrounding the Earth, but there are some gases that do the same kind of things that the glass would do. So there's gases in our atmosphere that let the visible light through but trap the infrared. One of them is water vapor. Right? You don't hear people talk about the water vapor being a greenhouse gas too much because that's something that's there naturally it's not the result of us. Probably the one you hear the most about greenhouse gas is carbon dioxide. So again, carbon dioxide is primarily the result. Carbon dioxide happens naturally in our atmosphere, but most of what's being added there nowadays is from burning gasoline and coal and natural gas. All those things being burned then produce carbon dioxide. So we're getting the amount of carbon dioxide in our atmosphere has increased substantially. And the more carbon dioxide in the atmosphere, that's like having more glass there. Again, it's going to trap that outgoing energy from escaping even more so. Now, so carbon dioxide is one that you probably hear the most about, and that's because there's the most of it. It's not actually one of the stronger greenhouse gases. These next few here are actually much stronger greenhouse gases, but their concentrations are lower. Now, methane usually comes from things decomposing or being digested. There's, methane happens naturally because things decompose and so forth naturally. But one of the big giant producers of methane are cows. Cows produce tremendous amounts of methane when they digest the grass and stuff. The more cows there are on Earth, the more methane there is. And methane is a very strong greenhouse gas. Or a place like a landfill. Sometimes if you go to landfills, you can smell, they smell. That's the methane being given off by the landfill from all the stuff decomposing there. With the methane, another problem is there's a lot of methane that's frozen in the Arctic areas, but as the Earth warms up, that's getting released, which is even warm things up even more. So that's a very dangerous one there. CFCs, or chlorofluorocarbons, that's a really, really strong greenhouse gas. We used to put that by accident in the atmosphere, and that actually, it's a greenhouse gas, but that was a problem for another reason. CFCs were putting a hole in the ozone layer, so they got outlawed. So there's really not very much of that's being put in the atmosphere anymore. But that is an extremely strong greenhouse gas. It does a really good job of trapping energy. Nitrous oxide, it's another greenhouse gas as well. Now, for the ones that are really strong, now the reason why I mention it is, let's say, because they could use stuff like CFCs if we ever needed to move to another planet. So let's say that we want to have humans start living on Mars. Mars is pretty cold. It's borderline, inhabitable. The temperatures are pretty cold there, though. But if we ever wanted to move there and we wanted to heat up the surface of Mars, if we spewed a bunch of CFCs in the Martian atmosphere, that would do a good job of trapping the sunlight and warming up the Martian climate and making it more preferable to us. So you could use gases like this to change the conditions on other planets if we ever got in a position where we needed to do that. All right, so that is energy nearest the atmosphere. Again, insolation is the energy we get from the sun. It's mostly visible light. How high of an angle it is in the sky is the main thing which determines how much insolation we get. Insolation hits the ground absorbs it, the ground gives off infrared energy that we call terrestrial radiation, and certain materials will let the visible light in but trap the infrared from leaving, and that warms it up inside. We call that the greenhouse effect.